Welcome to the Organic Chemistry Structural Review. What you should do in order to use this review the most useful way is make sure that you actually do these problems first completely on your own. Check your answers in the PDF, mark any that you get incorrect or don't understand, and then turn this video on. You can fast forward to any of the problems that you would like to hear an explanation for. I have clipped pieces of table R into this slideshow so that you can see the relationship between these molecules and table R to help you actually complete these structures. So I'm just going to walk through how I would draw each one of these and how I would know where to put functional groups, etc. Ethanoic acid. The oic acid tells me that I'm going to look for that same ending on table R. The example on table R is propanoic acid, which has 3 carbons. So the F in the name tells me that I only want to make 2 carbons. The oic acid tells me I have the Cu functional group. So I draw that on my end carbon. My last step is to make sure each carbon has 4 bonds. My functional group carbon has 1, 2, 3, 4 bonds already. My end carbon over here just needs to be filled in with those hydrogens. As you can see from the given answers, that's what my structural formula looks like. I've also given a condensed structural formula and a fully condensed formula. Remember, we condense these as a Cu group. Methyl ethyl ether is actually exactly on reference table R. Because it's an ether, we pop an O in the middle. This first methyl tells me I have a 1 carbon group. This ethyl tells me I have a 2 carbon group. So 1 carbon and 2 carbons. Oxygen set with 2 bonds. Each of these carbons needs 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. In its condensed form, it looks more like it does on the reference table. As you can see in the answer for the structural formula, we have our 1 carbon on the left side, 2 on the right, and those are filled up with H's. You can reverse this molecule. Doesn't matter as long as you have 2 carbons on one side, 1 on the other. Propanal, the Al ending, tells me that I'm talking about an aldehyde. Prop means 3. Again, this is the exact example that is on reference table R. To show it drawn out for your structural formula, we're going to draw our 3 carbons. Al ending means a double bonded O on our end carbon. Each carbon needs 4 bonds. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Keep in mind when you're condensing this, to differentiate it from the alcohols, we show that functional group is what I like to call a CHO. 1,2-dibromopentane. We're going to start with a pentane chain. This dibromo right here tells me that this is going to be one of my halides. In my halide example, I have 2-chloropropane. Propane indicates that we have 3 carbons in this molecule. The chloro is telling me what that halogen is. The 2 is telling me where it's attached. So I'm going to draw 5 carbons in a row. I'm going to choose to number from left to right, which would make this carbon 1, 2, 3, 4, 5. I have to attach 2 bromines, one at carbon 1 and one at carbon 2. These bromines can go up or down, doesn't make any difference. Then I need to fill in my bonds. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. If you needed to condense this down, you would just write the BRs in the chain, but mostly these particular problems are asking for structural formulas with the halides. Butanoic acid, similar to propanoic acid. This is an organic acid. But means 4. So I'm going to start with my 4 carbon chain. Oic acid means I need to have my Cu group on the end carbon, which is my double bonded O, my single bonded OH. That fills up that carbon's need for 4 bonds. My other carbons I just need to fill up. Keep in mind, again, we would condense this as a Cu group if we needed to have a fully condensed formula. Octanone means I'm going to have 8 carbons in a row, and I hear that oct prefix. The -one ending is a ketone, which means off one of the carbons, I have a double bonded O. In my example, it's showing the number 2. So carbon 1, 2 is where that double bonded O is. So I'm going to start by writing 1, 2, 3, 4, 5, 6, 7, 8 carbons. On carbon number 3, going from left to right, I'm going to make a double bonded oxygen. Now I need to make sure that everyone has 4 bonds. My first carbon has 1, 2, 3, 4. Second carbon, 1, 2, 3, 4. My third carbon already has 4 bonds. Fourth carbon needs 2 more, and I'll complete the rest of the molecule, which from there on out is pretty much just a straight chain alkane. When I show this in condensed form, I simply pull that O down into the molecule. You can see that right here. So you see the carbon that it is attached to is just in the chain like normal, and we just pull that O down there. Hexanediol is actually a little bit beyond what you need to know. It is closely related to an alcohol. This is just going to be what we call a diol because it actually has 2 OH groups in it. So hexanediol means I'm going to draw 1, 2, 3, 4, 5, 6 carbons in a row. This 1, 3 is relating to those 2 OH groups. So on my end carbon, I'm going to draw 1. On my second, third carbon, I'm going to draw another one. And then I just simply have to fill in my bonds. Butanol is a monohydroxy alcohol. Propanol, when we look at it, is a 3-carbon alcohol. So bute is going to be 1, 2, 3, 4 carbons. The 2 right here is indicative of where my OH group is going to go. So counting in, and it really doesn't actually matter on this one, it has to be just on one of your internal carbons. I'm going to attach my OH group and fill this in to make sure it has the proper numbers of bonds. Dimethyl ether means I have 2 groups, each one with 1 carbon in it. Ether, so if I'm looking at my ether example on table E, means I have that single bonded O in the middle. My methyl and ethyl in the example are telling me how many carbons come off of either side. So dimethyl ether is going to have 1 carbon on each side. Then we make sure our carbons have their 4 bonds. Oxygen's happy with 2, I'm not going to mess with it. If I needed to condense this, I would write CH3 for this carbon here, O for the O in the middle, and CH3 for my carbon on the other side. Diethyl ether, this is going to be a 2-carbon group coming off of each side. O in the middle, 2 carbons, 2 carbons, fill in my H's. Condense this, would be CH3, CH2O, CH2, CH3. Propanone, I'm looking at my own ending to tell me that this is a ketone. Now you might be thrown off by the fact that my example has a number and number 11 does not have one. But prop, remember, means 3. So this is a 3-carbon ketone. One of the rules of the ketone is that this double-bonded oxygen cannot be on an end carbon. So propanone can actually only really have its O right there. It's always 2-propanone. So we're actually allowed to leave that, that number off. So we can now make sure that we have 4 bonds on every carbon. 1, 2, 3, 4 for my carbon in my functional group. Fill in hydrogens on my 2 end carbons. If I wanted to condense this, CH3 for my first carbon, CO on my second carbon, and CH3 on my third carbon. Notice how this looks a little bit different than the ether does. If we actually wanted to compare this to like diethyl or dimethyl ether, the O we see is directly shown with that C it's double bonded to, whereas if we flip back to one of our ethers, this O is really next to the H from here, and the next C it's attached to, showing that it's just single bonded in that molecule. That's a little bit of a differentiation in how we write these. 2-butanone, it's a little bit more like our example because it has a number. That -one ending again tells me I have a ketone. But means 4 carbons. 1, 2, 3, 4. On my second carbon is where my double bonded O is going to go. To be fair, you could probably get away without putting a number on this one too, since that double bonded O has to basically be on carbon 2, depending on which direction you number it. You're going to fill in your H's. CH3CO, CH2, CH3. Often when you have to write a condensed formula, you're going to notice it's easier to draw the structural formula first and take it from there. Methylethanoate. The esters are hard. Make sure you tune in on your example. The O8 ending tells me I'm looking at my esters. Now the methyl part, you'll notice, methyl right here meaning 1 carbon, means off of that single bonded O, we only have 1 other carbon. So a lot of these I actually like to start by drawing my carbon chain. I actually like to start with the ethers by creating that functional group. So I have my carbon, my double bonded O, and my single bonded O. Methyl means I have 1 carbon coming off of the single bonded O. So over here, I'm going to draw 1 carbon. The ethanoate right here means that I have a 2-carbon chain, and that includes this carbon right here. So that's carbon 1, I'm going to attach to carbon 2. So methylethanoate should have a total of 1 carbon because of the methyl, then 2 more because of the ethyl, should have a total of 3, which as you can see, I have a total of 3 carbons in this molecule. Now I have to make sure everybody has 4 bonds. My carbon in my functional group has 1, 2, 3, 4. My carbon on the end needs some hydrogens. Oxygen, remember, is happy with 2. My other end carbon can hold 3 more hydrogens. If I want to condense this down, my first carbon on the left will become CH3. My functional group carbon I now write as COO, and then my end carbon is CH3. Ethyl pentanoate. So again, I see that O8 ending. I'm going to start by making my functional group. The ethyl right here, remember, is going to be a 2-carbon chain that needs to come off my single bonded O. So over here, I'm going to put 2 carbons. My pent right here means on the other side I have 5 carbons, including the one in my functional group. So I've already drawn 1, 2, 3, 4, 5. Now I have to make sure that I fill in, each carbon has to have 4 bonds. My carbon in my functional group is fine, oxygen's happy with 2. Take out my little arrow right there. And we're all set. To condense this down, CH3, CH2, 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 1, 2, 3, 4, COO, CH2, CH3. I had to count to check myself on that one. That's a lot of carbons. I should have a total of 2 plus 5, I should have a total of 7 carbons in this molecule. Methanol, nice easy one after that. OL ending, meth means 1 carbon. I draw 1 carbon. I don't need a number. It's the only place I can put my OH. Fill in those bonds. This can also be written as CH3OH. Moving on to naming. What we look for when we're naming is what is our functional group. When I look at this molecule, what stands out to me is this 1 double bonded O. It is not on an end carbon, it is in the middle of the molecule. A double bonded O in the middle of the molecule is indicative of the ketones. So when I look at my example here, I see ketone ends in O. It has a prefix from table P that tells me the number of carbons in a row, and a number telling me where to put my functional group. So I'm going to count my carbons in a row. 1, 2, 3, 4, 5, 6. I have 6 carbons in a row, which would make this a hexane chain. But instead of writing hexane, I'm going to write hexane, and then I'm going to put -one on it. I have to tell where this double bonded O is. I do need to check that I'm giving it the lowest possible number. So it might be considered to be carbon 3 if we go from left to right. If we number in the other direction, it would be on carbon 4. That's a higher number. So we'll stick with 3 and call this guy 3-hexanone. This molecule, what stands out to me is the fact that there are 2 oxygens, a double-bonded oxygen and a single-bonded oxygen with an H on it because it's on the end of the molecule. This is a Cu group. The other molecule that has 2 oxygens in it is going to be your ester. That ester functional group would have to have more carbons over here. We don't have that, so since this is on the end, this is considered an organic acid. In our example, propanoic acid, prop means 3. We can count 1, 2, 3 total carbons. This molecule has 2 total carbons, which would make it ethane. We're going to change that to ethanoic acid. This is a shrunk down condensed version of a Cu group. We still see that we have a total of 2 carbons. It's actually ethanoic acid again. This is also known as acetic acid, which we know to be vinegar, and that's actually how it's listed on your table of common acids. In this molecule, we see that we only have 1 O. So that leads me to believe I could have a ketone, I could have an aldehyde, I could have an alcohol, I could have a whole bunch of different things. What I need to look at is the fact it's not an OH, so that's not an alcohol. When I have an O right in the molecule like this, it might help me to kind of draw it out and see what's going on. If I were to draw that first C, which has 3 H's coming off of it, that kind of tells me there's got to be one more thing here, and it happens to be that O. My next C has 2 H's coming off of it, and then I have that CH3 on the end. So drawing this out helped me see that I don't have a carbon double bonded to that oxygen. These are all single bonds, which is how I was able to identify that this is an ether. I have 1 carbon on this side. I have 2 carbons on this side. This is actually just like my example down here, methyl ethyl ether. So that's my methyl, and that's my ethyl. And then ether, because of that guy right there. This is another example of an ether drawn out for you. We have 1 carbon here, 1 carbon here. So we would call those both methyls. So this is going to be called dimethyl. We don't have to say methyl-methyl. And then ether because of that single bonded O in the middle of the carbon chain. Oh, hey, look, it's an alkane. There's nothing here but hydrogens and carbons. We have all single bonds. Simply put, this is propane. Remember when things were that simple? This molecule is also all carbons and hydrogens. We're going to notice that this guy has a triple bond. So this is an alkyne. Works best for me to number in this one from right to left. So it's going to be 1-butyne. In this molecule, I see that I have an N. What's important to look for is if I also have an O. That helps me tell the difference between the amines and the amines. Because I don't have an O here, I only have an N, I know that this is an amine. To look back at how I would name this on table R, this is propanamine shown in the example because I have 1, 2, 3 carbons. The 1 is showing that the nitrogen is attached to that N carbon right there. So in this molecule, my nitrogen's attached to this guy. It actually doesn't matter quite so much because if I drew this out, I would say I have 2 carbons, 3 hydrogens on one, 2 on the other, and then this NH2 group. Whichever way you write this, that NH2 group will be on your first carbon. So instead of having propanamine, this is going to be ethanamine. And you actually can get away with no number since the nitrogen has to be on carbon 1. Now in this example, we see that we have a nitrogen and that double bonded oxygen. So this is more similar to propanamide. In this example, we have 2 carbons again, so this is going to be ethanamide. Our next example, what stands out as my functional groups are these guys right here. You gotta look carefully, make sure you see all of them, and note that they are not carbons. So I'm going to identify this as being a halide, and I look at my example on table R, which is 2-chloropropane. So first I'm going to go ahead and I'm going to number this guy, figure out how many carbons I have in a row. I could be pretty sure that that's the right direction to number in since my chlorines are all over toward my lower numbers. I have 8 in a row, 8 carbons in a row. So I'm going to call the end of this octane. Since I have 3 chlorines, I'm going to call this trichlorooctane. Actually, I think you get to ditch one of those O's. Sorry. Since I have, makes the name a little bit less awkward. Sorry, I had to double check that. So since I have 3 chlorines, I have to use the prefix tri in front of chlorine. I also have to tell people where they are. So I have 1 on 1, 2, 3. So this is 1, 2, 3, trichlorooctane. It's important that if I have numbers for 3 things, that I'm talking about 3 things. So 3 numbers here goes with that tri prefix there. Next example, I see that I have this double bonded O right here. This double bonded O right here is off of a carbon, but there's not another O right here. So that helps me differentiate. The fact that there's only 1 oxygen helps me differentiate that this is probably either an aldehyde or a ketone. The way that I know it's an aldehyde, not a ketone, is that this is an end carbon. I would have to have more carbons over here for this to be a ketone. So that double bonded O makes me, for my example, propanal. Propanal has 3 carbons. This molecule only has 2 carbons. So this is going to be an ethane root, only it's going to be ethanal. And last but not least, we got another Cu group right down here on the end. If we look at our total number of carbons, we have 1, 2, 3, 4, 5. So this is going to be pentanoic acid. I think the most common mistakes that students make when naming or drawing organic acids is not remembering to count this carbon right here. So potentially calling this butanoic acid, thinking that you only have 4 carbons. Or if you were asked to draw it, maybe throwing an extra carbon on there, thinking that you would draw 5 and then add your functional group. But this pent means you have a total of 5 in the entire molecule. That wraps up our structure and naming review. This was a very long and difficult exercise. Very important stuff, though. If you made it through this in one piece, you're probably pretty much an organic master. What's very important to keep in mind, you have a lot of responsibilities with this particular part of this unit, so make sure you use Table R to the best of your advantage, as well as your prefix table, Table P, and your hydrocarbon table, Table Q.